So in previous videos, I was investigating the locus of triangle centers of triangles A prime, B prime, C prime, which were projective images of Poncelet triangles inscribed in a circle and circumscribing a generic caustic. So ABC is a family, is a Poncelet family inscribed in a circle and circumscribing some generic caustic. And what I was doing is I was actually investigating the loci of these projective images of ABC under some fixed projectivity M. So you get A prime, B prime, C prime as a projective image of ABC under some fixed projectivity as I rotated the caustic rigidly about the center of the system. Okay, and we identified all kinds of very interesting uh, uh, invariants on the loci of three triangular centers: x2, the barycenter, x3, the circumcenter, and x4, only shown partially here, the orthocenter. Okay, so these invariants are described in the previous videos. Now, to assuage a piece of curiosity of mine, okay, I wanted to try kind of like the converse. Instead of ABC, now shown here as this red triangle, be inscribed in a circle and circumscribing a generic caustic, I wanted to know if there was an analog when ABC circumscribed a circular caustic and was inscribed in some generic ellipse. So ABC is a Ponceletian triangle family inscribed in an ellipse and circumscribing a circular caustic. Okay, now specifically what I want to observe is if I rotate this whole system about O, so now I'm not rotating the caustic, but I'm rotating the outer ellipse, so I can control that by alpha. If I rotate the outer ellipse, okay, about O, the caustic is going to stay put. Now, I want to actually investigate the loci of these rotated triangles, but once they are transformed by a fixed, as before, projectivity M. So right now my projectivity is just the identity matrix. Let's make it be a slight affinity. So I'm going to go ahead and change a little bit my off-diagonal elements here, as you see here. So this is an affinity, right? In fact, this is a scaling because these off-diagonal elements are 0. So just for the purposes of visualization, what you see now here is that the red ellipse, which is our final result, is the projective image under M of this rotated family of green ellipses and green Poncelet triangles. Okay, and the base family is precisely what is in light blue here. Okay, so I have the same phenomenon that I had before, but in a converse manner. So now I keep my caustic put and I rotate the outer conic with respect to the center of the caustic. Okay, thus emulating in converse fashion what I did before. Now you can see here that what I'm showing in this what is this, mauve or pink kind of locus, I'm showing the locus of x2 of the projective image, or these triangles here, which are projective images of the green ones, right? And as I apply a variable rotation to the system, I want to investigate what the locus, or what the family of loci of x2 is. I'm also showing here, just for reference, the locus of x2 of the non-projected family, which is a simple rigid rotation of the original one, right? So if I vary the rotation here, you can see that that green dotted green locus of x2 is just a rigid rotation, as you would expect, right? But what I'm interested in is what's happening to the post-projective locus, shown here as a magenta. So this is the word I was looking for, magenta ellipse. Okay, now let's see. So I'm showing here as well the product of the semi-axis of the magenta locus and the ratio of the semi-axis of the magenta locus. And right now I have an affinity. So let me go ahead and animate the rotation, and let's observe if there are any conservations for that family of loci. So it looks like in this case, the area of the locus of x2 is being preserved. Okay, let's go ahead and perturb a little bit my affinity. I'm going to put non-zero values on my entries here of the affinity. on my off-diagonal entries. Looks like the locus of x2 continues to preserve area, but it does not preserve the ratio of axes. How about the locus of x3? It conserves neither. How about the locus of x4? It doesn't conserve direction either, right? The locus of x4 conserves neither. Okay, so I think that this is a more restrictive setup. The invariants that we saw in the previous videos were more frequent. They're just more numerous than here. Right now, the only thing that I can conserve under an affinity is for the case of x2, where I conserve the area of x2. How about if I don't have an affinity? It's going to be much worse, right? So let's perturb these bottom entries here, the elation entries. And now you can see that not even x2 is conserving anything. How about x3? It doesn't conserve anything. In fact, x3 right now is a hyperbola. So let's look at x4, also hyperbola. Let's try to make these guys be ellipses again by not perturbing this too much, like so. Okay, so now I have, yeah, so it's transitioning. Let's see if I can make it be only ellipses like that. Yeah, it does transition to a hyperbola, but it doesn't matter. You can see here that during the phases in which it is an ellipse, it doesn't conserve anything, and then x3 neither. So just to stop this very quickly, I just want to say that I was hoping that if I just did the converse of the previous simulation, right? I had Poncelet family inscribed in a circle with a rigidly rotating caustic. We got all kinds of conservations for the loci of x2, x3, and x4. I said, well, maybe this property will also be verified if I have a Poncelet system which circumscribes a circular caustic and is inscribed in an ellipse. But the only conservation I'm getting here is for the case of an affinity and for x2, where area is conserved. Everywhere else, I'm not conserving anything. Okay? All right, see you on the next video. Thank you.